Welcome back to Biofate AI. Today, we're going to walk through a complete translational workflow, taking early preclinical data, predicting human pharmacokinetics, and simulating dosing regimens using our integrated suite of tools. We start in the scaling suite. This is found when you click on Interactive Tools on the left side of the navigator. The scaling suite is where we translate in vitro and animal data into human predictions. Let's characterize a hypothetical compound X. First, we input our physiochemical properties like molecular weight, log P, and log D. Now, let's look at IVIVE, in vitro to in vivo extrapolation. We'll select rat as a reference species and enter a microsomal intrinsic clearance of 50. Notice how the system instantly calculates the predicted hepatic clearance using the well-stirred model. If I go back and quadruple the intrinsic clearance to 200, the predicted human clearance updates in real time. We've run a metabolic stability assay using rat microsomes. We enter an intrinsic clearance of 50. Based on the well-stirred model, the app scales this up to predict human hepatic clearance. Take note of that result. Now, what if we had run this study in a dog or a monkey instead? Watch closely. I'm changing the species to monkey. If we go to the IVIVE tab once again, the predicted human clearance has changed immediately. Why? Well, that's because the app automatically adjusts the underlying physiological scalars: liver weight, hepatocellularity, and hepatic blood flow, specific to the monkey. You can see these differences in the scaling factors tab. The rat has a much higher blood flow per kilogram than the monkey. Biofate AI accounts for this biology automatically, ensuring your scaling is physiologically relevant. The same applies to protein binding. By chaining the fraction unbound from 10% to 1%, you can immediately see the impact on hepatic extraction. It's highly sensitive. Now, if you ever need a refresher on math, simply click the help icon. The AI mentor provides context aware explanations of the formulas and how to interpret these results. Next, for validating high clearance drugs, we can use the monkey liver blood flow method. By inputting the in vivo monkey clearance, we get a direct physiological scale up to humans. Here, you can also explore other scaling techniques like FCIM, MSA, and MLR. Depending on the situations and needs. Now, let's bring it all together. The extrapolation tab compares predictions from IVIVE, allometry, and other methods. The system automatically recommends the best fit, but you have full control. We'll stick with the auto-selected parameters. Here is a predicted human clearance, volume of distribution, and half-life. Now, watch this. With one click, we export these predicted human parameters directly into the PK simulator. No manual copying required. The simulator is already preloaded with the predicted values. Just enter the dose and hit calculate. And there is a predicted human concentration time profile for a single dose. Need more complexity? Switch to a two-compartmental model. We can easily add peripheral volume and intercompartmental clearance to see the distribution phase. This is the fastest way to visualize the shape of your compound's profile before you even run a clinical trial. Now, let's look at the retrospective analysis using the PK models engine. This is for when you have actual experimental data. I'll load some rat IV data. First, we run a non-compartmental analysis. Press calculate and instantly we get a lambda z, AUC to infinity, clearance and volume. But does a compartment model fit better? Let, let's fit a two compartment model to the same data. The engine runs an elder meat optimization and there we go. The fitted line overlays the observed points and we get our micro constants K10, K12 and macro constants alpha, beta. But for a student or a chemist, what do these numbers actually mean? This is where Biofate AI shines. Click on the AI interpreter. The AI analyzes this data in real time. And look here, it interprets the clearance value, telling us if it's considered high or low. It looks at the volume of distribution and explains whether a drug is distributed into tissues or not. It even provides an educational breakdown explaining how you can estimate these parameters manually using the slope of the curve. It turns every analysis into a learning moment. Moving to the clinic, we need to understand multiple dosing. Let's look at the steady state simulator. Here, we have a drug with a 12-hour half-life, dosed once daily. The accumulation is minimal. If we dose more frequently, say every 6 hours, watch how the concentration accumulates significantly over time. It takes about 5 half-lives to reach a steady state. To reach therapeutic levels instantly, we can check the Simulate with Loading Dose tool. It calculates the required bolus to hit steady state targets immediately. For safety assessment, we use the TK simulator. We can simulate dose proportionality across 3 dose levels. The tool plots log Cmax and log AUC against log dose. It automatically calculates the slope. If the slope is greater than 1.25, it flags potential saturation of clearance, a critical safety insight. Finally, for advanced species scaling, we have the PK shape engine. Instead of just scaling numbers, this scales the entire curve. By normalizing time and concentration using Dedrick or Wajima plots, we can superimpose animal profiles to predict the exact shape of the human curve. So, from specific activity inputs to steady state simulations, Biofit AI provides a complete toolkit for the DMPK scientist. Try it today to accelerate your drug discovery programs. If you learned something new from this video, please don't forget to like and share this with someone who can benefit. Subscribe to our channel for more information about the app, and the app's link will be provided in the description box. Thank you so much for watching and happy experimenting.